Okay, we're going to finish by looking at some of the basic facts about eigenvectors and eigenvalues. And some of these things we're going to defer to next week because they kind of segue into more advanced topics, but we'll get started and cover some of the basics now. So first of all, we want to define what an eigenvector and eigenvalue are, and we have to have a square matrix in order to be able to talk about eigenvectors and eigenvalues. And we're going to say that some non-zero vector x that satisfies the matrix equation ax is equal to lambda x, where lambda is some real number. It can be complex, but we're going to talk about real eigenvalues here, okay, for the most part. Although real matrices can have complex eigenvalues, so I should probably be a little more general and say that lambda can be a complex number, okay? Then this pair, lambda and the vector x, is said to be an eigenvalue-eigenvector pair. And sometimes we kind of abbreviate this as an eval-evar pair. All right, some important properties of eigenvectors and eigenvalues, we can prove some of these, is that the trace of a matrix, which is the sum of its diagonal elements, is the sum of the eigenvalues. That's always true for every square matrix. And the determinant of A is equal to the product of its eigenvalues. So if you think about it for a second, we have another way of saying that a matrix is invertible. We can say a matrix is invertible if and only if its determinant is not zero, if and only if all of its eigenvalues are non-zero. Okay, some of the other facts that we need to know is that A is non-singular, which is just what we said a second ago, if and only if all the eigenvalues are non-zero. Okay. A very important fact is that whenever we have a symmetric matrix, we can always choose the eigenvectors in such a way that they're orthogonal. That's a very important fact. And another important fact is that if we have distinct eigenvalues, their eigenvectors are perpendicular or orthogonal. In other words, the inner product of two eigenvectors that correspond to distinct eigenvalues is zero. And you can prove the statement in blue, and it's a good idea to try that, to try to prove this, okay? This last statement. Okay, how do we compute eigenvectors and eigenvalues? Well, if the matrix is small, we know how to do this. We generally find the eigenvalues and then we solve for its corresponding eigenvector. So how do we solve for the eigenvalues? Well, we solve for the roots of the determinant of A minus lambda times the identity matrix is equal to 0. This gives us an nth order polynomial in lambda, which is called the characteristic equation. And the n roots of the characteristic equation are our n eigenvalues. And then of course we go back and we look at the solutions of A minus lambda I quantity times x is equal to 0. And so those solutions x of that homogeneous system are going to be the eigenvectors. And you can easily see why that's so. If you bring over the minus lambda identity times x, we get the eigenvector eigenvalue equation. Okay. Now what if the matrix is big? Then we have a problem. Because for example, computationally, how would we even set up what the characteristic equation is, let alone solve it? Okay, it's quite complicated. Well, it turns out there's a very nice method called the power method. It's based on a famous theorem called the Perron-Frobenius theorem. And this was actually one of the tools that the makers of Google used in their page ranking algorithm. This is a very important fact. It says that if you start with a square matrix A and you take some random vector and you construct this sequence of vectors, it converges to the eigenvector of the largest eigenvalue. So this is a mathematical theorem. Okay? So we construct this sequence of vectors and they converge to the vector of the largest eigenvalue. And then of course finding the eigenvalue is easy. We simply just multiply our final vector that we get after the iterations times A, and we end up getting the eigenvalue. Now, when we want to find the next eigenvector and eigenvalue, we simply subtract off lambda in from A, where lambda was the largest eigenvalue. And we simply repeat our method with this new matrix, and this will find us the eigenvector for the second largest eigenvalue, and so on and so on and so on. Okay? I don't want to go into too many theoretical details, so I just want to tell you about a few applications that we're going to look at. The first application is in dynamical systems. So we can have what are known as linear dynamical systems, which I'm going to define in a moment. But basically we know that if we have a linear differential equation in one variable x, so it has this form, we can easily solve that, right? In fact, with our calculus we just did in the last section, we can easily show that the solutions have the following form. Okay, initial condition x naught times e to the at. Now, it very often happens that we have more than one differential equation. We could have a system of linear differential equations like this, okay, which we can write in the following form. And it just so happens that the form of the solution for this differential equation looks very much like what it does if we're looking at that equation for one variable, except you notice in place of the scalar a, we have the matrix capital A. So we can actually talk about the exponential of a matrix. We're going to show how that's defined once we've worked with eigenvectors a little bit more. Now, why is that useful? Well, because there is a fact that says, and this is based on some facts about eigenvectors we're going to talk about next week, that shows that given this exponential form of the solution, it can be rewritten like this. Okay, the eigenvector vi times e to the ith eigenvalue times t, and there's going to be some weight c sub I, and of course these weights are going to depend on the initial conditions. Okay, now why is that a useful way of writing the solution? Well, because if we want to look at the asymptotic behavior of the system, it's easy to see that as the t goes to infinity, the term that's going to win out is the term that contains the largest eigenvalue. Okay, so this vector converges asymptotically to the largest eigenvector. That's the idea. Okay, a second application we're going to do is when we're looking at covariance matrices, when we're doing principal component analysis. And if we look at the variance of some random vector w that is basically a vector of two random variables x and y, we know that the covariance matrix looks as follows, okay, where sigma is the covariance matrix. Okay, it's a symmetric matrix, which is very important. So this is where all of these facts about symmetric matrices that we want to use come in when we're dealing with covariance matrices, because it just so happens that when we have a symmetric matrix, the eigenvalues and the eigenvectors are orthogonal. And so it turns out that we can re-express the covariance matrix as follows. Okay, u and v are going to be basically orthogonal to each other. Okay, they're going to be stochastically independent. And so we end up getting the following form for the covariance matrix, which is much cleaner. And there's a geometric interpretation, and this is kind of where principal component analysis comes in. It has to do with the fact that when you look at the covariance matrix, you can show mathematically that you can always re-express the covariance matrix as basically the equation for an ellipsoid. Okay, and so the principal axes of these ellipsoids are going to be our principal components. Okay, this is where the notion comes from. All right, and so this is going to be something that we're going to use a lot when we're analyzing the covariance matrix. Okay, that's it for the week 1 material. I will give you some problems and then we'll go on to the more abstract material next week.